Hello, it's a little single IC project using just a CMOS 4093, CD4093. Now it could equally work with a 40106 and that could work even better. It's touch switches. I don't think you can see that. Oh yeah, you can see the lead in the camera, yeah. So there are a lot of imitation or very poor quality touch switches about in other little modules, and the commonest one I can see appears to be based on, it's not a touch switch so much as a hum detector. It's a bit like detecting amplifier hum on an open input. In fact, let me just switch the time base on the scope. I've got it set up to read the signals on this thing, which is very high speed, and I want to be low speed, so you can see hum. Yeah, so the simple touch switch boards, the hum detectors, they detect the hum, the noise pickup, when you touch an open input and you're ungrounded. Basically, you're touching the base of a transistor or the gate of a FET, and it's just picking up noise, which is okay under some conditions. But if you are grounded, so like if I touch the probe ground at the same time, that's picking up. As soon as I touch ground myself to that, it goes away. It only works if it's different to the ground reference of whatever or whoever's touching it. So it's not very good for handheld devices or things that are earthed, because if you're earthed as well, or if you're holding it, there's no hum or no difference between the two voltages. This is a true capacitive touch switch of one type. Let's reset the scope. This is the circuit. This is based on an oscillator, simple oscillator, one CMOS Schmitt trigger gate or inverter. You can see in this all the, I'm using a 4093 because those are the ones I have. I don't have any 40106s, but they're only being used as inverters with both inputs connected together. Use a Schmitt inverter, just single input, single output, it would do exactly the same thing. So it's a simple oscillator, capacitor ground, resistor for feedback. That's running at about 100 kilohertz with those values. We put the scope ground on the circuit ground and touch the oscillator output there. That's the waveform. So it's 20 microseconds per large division on the scope, and it's about 2 cycles in that, so 10 microseconds a division, 10 microseconds a cycle rather, 100 kilohertz. So that's producing a square wave at pretty much full supply voltage, or whatever that is. That then feeds through to each detector circuit, each touch detector, a limiting resistor just to protect the output, and 2 capacitors. Now you see this is only 100 picofarads, the small, fairly low value capacitors. The touch point is the junction of the two. There's no DC connection. It's a very high impedance to low frequencies, so it's not affected by hum and things like that. And then that feeds into a simple 2-diode rectifier and a pull down resistor and a smoothing capacitor, a tiny smoothing capacitor. It's just 1 nanofarad, because it's a very high frequency signal, so it doesn't take much to keep a stable voltage on it. And into the input of another Schmitt inverter or gate. When it's not being touched, the signal goes straight through there, is rectified and causes a voltage at the input, so the output goes low. If I find the rectifier output on this, which is there, see that's the voltage at the input on pins 1 and 2 on that gate. If I touch the pad the voltage reduces. And you see, depending how firmly I touch it, depends how low the voltage goes. If the voltage goes below the switching threshold of the gate, the output goes high. If you look at the actual AC voltage there, you see that's the AC voltage through the two capacitors at the input to the diode. I'm actually touching the diode point at that. Again, if I touch that, it changes, reduces. Now the oscilloscope capacitance is loading it a bit, and that's why it's not switching off again. It's not going quite back to high enough voltage to switch back on. That's the only thing with this simplified design, because it's got very high hysteresis. Now the difference between the switching at each polarity on the gate, in fact you can see that if I look at the oscillator waveform, you can see the difference in the voltage between the output switching high and low as the capacitor charges is a couple of volts, 2 or 3 volts. If you wanted to make this more sensitive or more controllable, you could use a proper comparator rather than just the CMOS gate for each input, and that would allow you to have this signal going to one input and say a potentiometer preset across the supply going to the other input, so you could set the exact voltage that this switched at and control the sensitivity. Or you could even use an opamp as a buffer, and use a CMOS rail-to-rail opamp, so you're seeing this whatever voltage is on the detector and feed that through a buffer to an analog input on a microcontroller. Now you can actually calibrate it to no touch and touch, no matter what other capacitance is on the circuit. Now there is one other big difference between this and the hum detector types. This only works if it is at least capacitively grounded to the person or thing that's touching it. Now, because this is battery powered, it's now completely floating. I've taken the scope earth off. Notice it doesn't do anything, and that's because there's no return path from it. If I put the scope on the ground with the scope input on the ground, you can see it's picking a lot of random noise and stuff, and a bit of the waveform. If I touch one of the pads, the oscillator waveform goes right up, because effectively, rather than it building up a voltage on the detector, the oscillator voltage is just going straight through. I'm grounding the live side, if you like, so the other side now has the voltage on it. It's like touching one terminal of a battery to ground. The other terminal will have the voltage on it. I'm grounding that, so the other side's got the voltage. So you do need a ground connection of some sort. It doesn't have to be literal ground, but if it's something that's handheld, like if I touch this wire, so that's got a connection back to me now from the circuit ground, it works. That could equally be a casing of some sort, anything with enough capacitance to the user's body so it picks it up and it has an effect. And again, with proper comparators or an op-amp and monitoring the voltage, that will be creating some voltage difference, and with a more sensitive detector that would pick it up. It's just not enough to trigger this circuit that needs a lot of voltage change. It needs a couple of volts change on the input, and it won't be giving that much, and I can't demonstrate that without touching it with the probe, which will make it work differently. But it will be changing to some extent doing that. In fact, I don't know what happens if I touch one of these and touch the other one. Yeah, you can see that makes me touching one makes the voltage on the other one change. So it is having some effect, but it's just not enough for that particular crude large hysteresis detector to pick up. Anyway, I hope that's of interest, and as usual I'll put put this PDF circuit in a link so you can have a look and see how it works yourself. I mean, the layout's a bit complex on here, but hopefully you can see some idea of what it's doing if I zoom in a bit. That's the oscillator. I've used the same pins as on the drawing. So that's the oscillator, resistor and capacitor. I think I've got the wrong value up there. For some reason I've left that. No. That's not 1 meg. That's that would make it rather low frequency. Sorry about that. That is 10k. Okay, sorry about that. Yeah, so I'll correct that before I post it. Yeah, it's a 10k resistor and a 1N capacitor. Oh, I'm glad I looked at that. So that's the oscillator. Then that's one detector circuit, the one that connects to pins 1 and 2. That's the 10k series resistor that feeds from the oscillator to the first capacitor. That one. That links to the second capacitor and the touch sensing wire. Then the second capacitor links back to the junction of the two diodes, one of which is from ground, and the other one of which goes to the input with the smoothing cap and the 1 meg discharge resistor. So hopefully you can make sense of that. And then the other one is effectively the mirror image for the second channel. There's a spare gate on there I'm not using. I could have put a third one on that. The oscillator can drive numerous sensors. You can add those. If you use a 40106 with this circuit, you could have one oscillator and 5 detectors all using a single IC. Well, what's happening with the lighting? It's flickering a bit for some reason. I hope it's not causing a problem. Anyway, I hope that's of interest, and another single IC novelty one to follow. Anyway, thanks for watching.